Why does your body move forward when a car suddenly stops? Why does a balloon fly everywhere when you let it go? And how does a rocket blast into space? The answer isn't magic. It's physics. 3 laws. 3 simple rules that control motion itself. Newton's laws of motion. Hey everyone, and welcome back to the channel. Today, we're diving into something that governs literally everything that moves in our universe. From a tiny speck of dust floating in the air to the majestic dance of planets in our solar system. We're talking about the 3 fundamental principles discovered by the legendary Sir Isaac Newton. These aren't just some dusty old rules from a textbook. They are the invisible strings that pull and push our world every single second. So, buckle up, because by the end of this video, you'll see the world in a whole new dynamic way. Let's start with a situation we've all experienced. You're sitting in a car, maybe scrolling on your phone, and the driver suddenly slams on the brakes. What happens? Your body lurches forward, right? It feels like you're being thrown towards the dashboard. Have you ever wondered why that happens? It's not magic, it's physics, and it's the perfect introduction to Newton's first law of motion, often called the law of inertia. So, what is this law? It's beautifully simple. An object at rest will stay at rest, and an object in motion will stay in motion with the same speed and in the same direction, unless acted upon by an external force. Let's break that down. If a book is sitting on your desk, it's not going to spontaneously fly across the room. It will stay put at rest forever, unless you or something else, like a gust of wind, applies a force to it. The same principle applies to moving objects. Imagine you're out in deep space, far away from any planets or stars. If you throw a baseball, it will continue moving in a straight line at a constant speed, forever and ever, because there's nothing out there to stop it. No air resistance, no gravity. It will just keep going. This resistance to a change in motion is what we call inertia. Everything with mass has inertia. The more mass something has, the more inertia it has, meaning it's harder to get it to start moving. And it's also harder to get it to stop once it is moving. Think about it. It is much easier to push a shopping cart than it is to push a car. The car has more mass, so it has more inertia. It resists the change from being at rest. Now, let's go back to our car example. When the car is moving, you and the car are moving together at the same speed. You are an object in motion. When the driver hits the brakes, the external force stops your body from continuing to move with the car seat. But your body, due to its inertia, wants to keep moving forward at the speed you were just traveling. That's why you feel that lurch. Your body is trying to obey Newton's first law. It's resisting the change in motion. This is also why seatbelts are so critically important. They provide the necessary external force to safely slow you down along with the car, preventing you from continuing your forward motion into the dashboard or windshield. It's a lifesaver, all thanks to a deep understanding of inertia. Okay. So the first law tells us that we need a force to change an object's motion. But what exactly happens when we apply that force? How much does the motion change? This brings us to Newton's second law of motion, which is probably the most famous of the 3, because it comes with a neat little equation. Force equals mass times acceleration, or F equals ma. Let's unpack this powerful formula. It connects 3 key concepts: force, mass, and acceleration. Force is the push or pull on an object. Mass, as we discussed, is basically how much stuff is in an object. And acceleration is the rate at which an object's velocity changes. It could be speeding up, slowing down, or changing direction. The law states that the acceleration of an object is directly proportional to the net force applied to it, and inversely proportional to its mass. What does that mean in plain English? 2 things. First, if you push or pull on an object harder, it will accelerate more. If you push a toy car gently, it speeds up slowly. If you give it a really hard shaft, it accelerates much faster. The bigger the force, the bigger the acceleration. This makes perfect sense, right? Second, for the same amount of force, a heavier object will accelerate less than a lighter one. Let's say you have a golf ball and a bowling ball. If you push both of them with the exact same amount of force, which one will speed up faster? The golf ball, of course, because it has less mass. The same force produces a much greater acceleration. The bowling ball, with its larger mass, will barely budge. This is why it takes a massive amount of force from powerful rocket engines to lift a heavy spacecraft off the ground and accelerate it into space. The rocket has an enormous mass, so it needs an equally enormous force to achieve the necessary acceleration to escape Earth's gravity. F equals ma is at work everywhere. from hitting a baseball to designing a sports car. Now we arrive at Newton's third law of motion. You've probably heard this one before. For every action, there is an equal and opposite reaction. This law is all about pairs of forces. It says that forces always come in pairs.
If object A exerts a force on object B, then object B simultaneously exerts a force on object A that is equal in magnitude and opposite in direction.
This can be a little tricky to wrap your head around at first, but examples make it crystal clear.
Imagine blowing up a balloon and then letting it go. The air rushes out of the back of the balloon.
That's the action. The reaction is that the balloon itself is pushed forward, zipping around the room. The force of the air pushing backward is equal and opposite to the force on the balloon pushing forward. Think about how a rocket works.
It's the same principle, just on a much grander scale. The rocket pushes hot gas out of its engines downward. That's the action.
The gas, in turn, pushes the rocket upward with an equal and opposite force. That's the reaction. The rocket isn't pushing against the ground. It's pushing against its own exhaust. This is why rockets work perfectly well in the vacuum of space, where there is nothing to push against. This law is also the reason we can walk.
When you take a step, your foot pushes backward on the ground.
That's the action. The ground, in response, pushes forward on your foot with an equal and opposite force. That forward push from the ground is what propels you and moves your whole body forward.
When you're swimming, you push the water backward with your hands and feet. The water pushes you forward. When a bird flies, its wings push the air down and backward. The air pushes the bird up and forward.
Every single time something moves, there's a pair of forces at play. So let's recap. Newton's first law: objects resist changes in their state of motion. That's inertia. Newton's second law: the more force you apply, the more an object accelerates. But the more mass it has, the less it accelerates. F equals ma. And Newton's third law: for every action, there's an equal and opposite reaction.
Forces always come in pairs.
These three simple, elegant laws form the bedrock of what we call classical mechanics. They allow us to predict the path of a thrown ball, calculate the orbit of the moon around the Earth, and design bridges, cars, and airplanes.
They describe the dance of motion that is constantly happening all around us.
The next time you see a ball bounce, a car turn a corner, or even just take a simple step, you can smile and know that you understand the fundamental rules of the game.
You're seeing Newton's genius at work. Thanks so much for watching today. I hope this has made the world of physics a little less intimidating and a lot more fascinating.
If you enjoyed this video and learned something new, please give it a thumbs up and consider subscribing to the channel for more deep dives into the wonders of science.
Don't forget to hit that notification bell so you won't miss our next video.
Until next time, stay curious,